This is Kwang Pyo-hong from Gwangun Environmental News. This summer, record-breaking heat waves have caused the rapid spread of algal blooms. Due to global warming, algal blooms are expected to worsen over time. Team number 4 of Gwangun University's Environmental Engineering capstone is reportedly working on solving this issue. Let's connect with researcher Woo-ju Jung.
Hello, I'm researcher Jung Woo-ju. Methods to remove algal blooms, including effluent losses using hydrogen peroxide and clone disinfection. Effluent losses is eco-friendly, but the aggregated algae may resurface over time and does not address the root causes of algal blooms. Hydrogen peroxide, a strong oxidant, is effective for short-term solutions, but may negatively affect aquatic organisms. Clone disinfection has a strong sterilizing effect, but byproducts generated after treatment can harm aquatic ecosystems and humans. And high clone levels can threaten biodiversity. Considering these limitations, we decided to use photocatalyst technology, which is sustainable, highly effective, and cost-efficient. However, photocatalysts also have certain limitations in addressing algal bloom issues. TiO2, one of the commonly used photocatalysts, mainly absorbs UV light, making it less effective in using sunlight to remove algae in lakes. Algae mainly spread on the water surface, but powdered photocatalysts tend to sink over time. Additionally, at depths greater than 0.5 meters, visible and UV light penetration decreases by 80% and 99%, respectively, reducing the effectiveness of photocatalysts. Moreover, powdered photocatalysts are difficult to recover and recycle, potentially causing secondary pollution. To solve these issues, our team decided to use nitrogen-doped TiO2, combined with hydrogels and 3D printing technology. Using nitrogen-doped TiO2, we ensured high efficiency even under visible light. By combining it with hydrogels, we designed a system that effectively removes algae from the water surface and can be easily retrieved and reused. We also used 3D printing technology to create structures that float on water and are easy to retrieve.
Yeah, I've heard about using nitrogen-doped TiO2 combined with hydrogels and 3D printing. It's very exciting. Now, let's hear about the method for sample preparation.
First, we investigated the algal bloom contamination around our school by examining a nearby stream, Uicheon. We collected water samples directly from the lower reaches of Uicheon and analyzed them according to standard testing protocols. The standard testing method for measuring chlorophyll is as follows. First, 2 liters of the sample are filtered using glass fiber filters. Second, the filter paper and 10 ml of dilution acetone are ground using a mortar and pestle. Third, the mixture is left overnight in a dark place at 4 degrees Celsius. Fourth, the sample is centrifuged at 500 grams for 20 minutes, and the supernatant is transferred to a cell for further analysis. Finally, the absorbance of the sample solution is measured at 663, 645, 630, and 750 nanometer, and the results are calculated using the following formula. However, the measured chlorophyll concentration in Uicheon was rated as very good. Thus, we determined that it was unstable for verifying our idea's effectiveness. So, we purchased chlorella and prepared a dilution chlorella solution for use as a sample. Analysis of the chlorella sample according to standard testing protocols resulted in a poor rating, making it a stable sample for further experiments.
Oh, you must have gone through a lot of effort collecting samples yourself. Next, how did you create a photocatalyst to remove algal blooms?
The photocatalyst P25 is an affordable and basic photocatalyst. However, it is highly efficient over under UV light, which limits its practical application in rebels. To address this, we referred to various papers and found that nitrogen-doped TiO2 has a lower band gap than P25, making it more responsive to visible light than UV light. Therefore, we decide to use nitrogen-doped TiO2 to overcome these limitations. Here is the process of producing nitrogen-doped TiO2 photocatalyst based on the repressed studies. TiO2 and urea were mixed in a fourth ratio in ethanol and stirred for 24 hours. The resulting slurry was dried and concentrated in the oven. The dried solid was transferred to a mortar and ground, then heated in a 600-degree kiln for 6 hours to produce nitrogen-doped TiO2 catalyst. We conducted comparative experiments to verify the improved efficiency and response snap under visible light. The results show the efficiency of P25 and nitrogen-doped TiO2 in removing methylene blue under different light wavelengths using UV-Vis spectrophotometry. As you can see, nitrogen-doped TiO2 showed significantly greater efficiency compared to P25. Hence, we decided to use nitrogen-doped TiO2 photocatalyst for removing algal blooms. Additionally, it demonstrated the highest efficiency at 525 nanometer in the visible light range, which we chose for this experiment.
Nitrogen-doped TiO2 indeed shows high efficiency even under visible light. You are combining it with hydrogels?
Yes. Hydrogels combined with photocatalysts can address several limitations of photocatalysts. They enable the removal of algae on the water surface and are easier to retrieve than powdered photocatalysts, offering environmental and economic benefits. Here is the process of producing hydrogels combined with photocatalysts. First, we mixed 200 ml of distilled water with nutrient agar and heated it 80 degrees. Next, we added 3.6 of photocatalyst to the heated agar dispersion and evenly distributed it. The mixed agarose titanium dioxide solution was cooled at room temperature to form cross-linked hydrogels. Using the prepared hydrogel photocatalyst, we conducted an experiment to remove a 24 diluted chlorella sample under 525 nanometer light. After a 2-hour experiment, we observed a removal efficiency of 14.42%.
14.42% removal efficiency in just 2 hours? That's lucky. And you're applying 3D printing to this? Oh my god.
To enhance the long-term efficiency and reusability of hydrogel photocatalysts, we utilize a 3D printer to create a custom structure. The design was crafted using the SketchUp program, and printed with a 3D printer after processing it with CUDA. A lightweight structure weighing 42.55 grams was created using filament material. The design features a broader surface area to enhance buoyancy, ensuring it floats well on water as confirmed through experiments. The structure incorporates an empty central space, providing an optimized environment for the hydrogel photocatalyst to effectively remove algae blooms. A mesh was attached to enable the hydrogel photocatalyst to target and eliminate algae located deeper in the water column. This setup not only ensures a stable environment for recovering the hydrogel, but also protects it from contamination caused by algae curses.
So you utilized 3D printed structures to enhance the long-term efficiency and reusability of hydrogel photocatalysts? With Capstone Team 4, it seems we no longer need to worry about algal blooms in the future. This concludes our news segment. Thank you.